So, very good afternoon to you all. So, welcome to the sixth session of the course Geoprocessing using Python. So, now we will discuss about various processing on the raster data, like how do we clip or subset the raster data using GDAL, then how do we resampling, or how do we stack multiple bands together to create a RGB or colored image, and so on. So before going to that, I just wanted to show you, like, actually yesterday when we were trying to make different false color composites, so we were facing an issue, or the same issue we found, like during when we tried to read a net CDF file. So actually these problems were due to the older version of GDAL. Actually, initially I had written the code using new version of GDAL, but because of some issue that I could not install the latest version of the GDAL. So right now I have installed the latest version of the GDAL in this system. And now let us discuss first about creating this. First we will see how do we create a false color composite using GDAL, and later on we will see that how do we read a net CDF file, and then we will continue to the today's lecture. So here I am just changing my working directory to the directory available, and then this is as usual all the usual imports, and we will just directly go to the part where we were just reading the file. So before that, if we discuss about the bands, because this is the image which I am going to display here. It's the band of is an image acquired by list 3 sensor of Resource 2 spacecraft of the ISRO. So if you talk about the bands of list 3, so in list 3 there are 4 bands. So band 2, actually that they call the band 2, 3, 4 and 5, but in GDAL parallels we will be calling them band 1, 2, 3 and 4, but in the spacecraft nomenclature they are calling them band 2, 3, 4 and 5. So band 2 corresponds to GDAL's band 1, 3 corresponds to GDAL's band 2, 4 corresponds to band 3 and 5 corresponds to band 4. So band 2 is green, band 3 is red, band 4 is NIR and band 5 is SWIR. Right, now suppose if we want to create a false color composite, like a standard false color composite. So before that I'll just read the file. So file name is not defined. And I have just read the file. Okay, and now let us read this. So now what we are trying to create, we are just trying to create a standard false color composite. First of all, let me check if DS is there. So DS is read correctly. So now I just want to create a false color composite. So standard false color composite. There what we want the near infrared band reflectance to be represented as red, green to be represented as blue, and red to be as green, right? So for that, now once we have opened the file, now we will call the function ds.read as array. So read as array, if you don't pass any argument to read as array, it reads all bands from that image. Like then otherwise, if you want to read some specific band from your data set, then you can pass it another argument called band underscore list. So band underscore list, you need to pass a list, like all bands you want to read, right? So now here we want to read 3 bands. One is NIR, green and red. So NIR bands corresponds to, as we explained that in the list 3 image, so band 3. So band 3 is NIR because the bands in list 3 image are like green, red, NIR and SWIR. So So green, NIR, red and SWIR. So 3 is NIR band. So NIR band, that will go into the band 0. Then green is band 1. Then we are reading band 1. Then we are reading band 2 or red. So in this sequence we are reading the bands NIR, green. So actually we are supposed to read it like 3, 2 and 1. Sorry. So NIR goes to the red band, and red goes to the green band, like band 2, and last one blue goes to the green. So if I do this, now suppose if I visualize this all together. So before that, actually as I explained that when we need to plot a multi-band image using matplotlib, the data needs to be in certain shape. Like if I see the shape of this data, so presently it is in the format like first comes the channels, then width and height. But matplotlib, when we are going to plot 3-dimensional or what you call RGB image or 3-band image, then in that case we need the data in the different format like then width, height and channels. So for that we need to permutate the access of our data. So permutation can be done using np.transpose. So np.transpose, here what we are doing, so 1 and 2 we are same, 1 and 2 axis. So 0th axis is now this channel color axis is coming to the last. So by this transpose we are permutating the access of our data. Now if you see the shape of data, it is like 1151 1151 by 3. So now if we visualize this image, it comes like, so this is a standard false color composite what we can see. Similar way, now suppose if we want to create another composite like suppose if you want short wave infrared to be in the red, NIR in green and green in blue. So this is the combination like multi-data ds.read as array. Band list you can pass it like first in red band we want short infrared, that is a band 4. Then near infrared we want to be in the green, and green we want it to be in the blue. So if you do this way, and then later if you permute the axis and if you visualize the data looks like this. This is also one of the standard false color composites. So similar way you can create any kind of false color composite. So here you can see this is the Nainital lake and this is some water body. So this way we can visualize or create any false color composite. Like if our data set contains more than 3 bands, then we can make any combinations of these electromagnetic bands for making a false color composite. So now let us see that how do we read a netcdf file. So same thing we are going to do. So this data is downloaded from the Mosdax archival. So this is some this is a bit of old forecast data, but anyway we can just see that how does that data look like. So anyway this is same thing. No, I need not do anything. So this is my file. So now if I read this file, so for reading a netcdf file we need to call this function GDAL or what do you call multi-dimensional data GDAL.openex. So openex, then we need to pass it 2 arguments, like one is the name of the file which you want to read and GDAL and function called GDAL.of multidim raster, like GDAL.type multidim raster. So once this is done, and if we see ds, so it has read it properly. Now first thing what we need to extract, like in HDF case we were getting get sub data sets. So in this actually in netcdf file the data is organized in the form of groups. So first thing we need to extract the root group so that we can get all the subgroups of that. So if I call ds.get root group, I will get the root group from that. And now in this root group I can get like which all multi-dimensional arrays are there. Suppose now which all variables are available in this netcdf file. Suppose if you want to extract on this root group, I will get multi-dimensional array names. So if I call this, then see these are the different multi-dimensional arrays available in this netcdf file, like latitude, longitude, level 2 time, T2 maybe T2 is temperature, then PSFC some parameter may be there, rain, accumulative rain, then like this cloud, another humidity, wind speed and wind direction. So these all variables are available there. Now suppose if we want to read the temperature array from this, so then we can do root group dot openMD array, and pass it the name of the variable which we want to read. So once this is done, then we can call this will be a data set again. So if we call this tempds.read as array, and because I think this the temperature is in Kelvin, so if we subtract 273 from this, we get the temperature in degree Celsius. So this is the shape. So if you see the shape of this data, it is shape of like 25 into 1 into 900 into 900. So this is like prediction for next 25 for 25 time what you call time slices. So every time is like every 3 hours for next 25, so 25 into 3 for next 25 or 42 hours forecast is available in this data. Now suppose if we want to visualize how does this data look like, then like same matplotlib you can plot it. Similar way you can do for any other thing, like suppose if you want to see all forecasts of this data, so then you can loop over it. So this way we can see that this is like at time T0, at time T1, time T2, time T3 and so on. These are the forecasts for next 72 hours. So this way you can visualize any variable in netcdf file. Then similar way like you can visualize other parameters like wind speed, wind direction, anything like those you can convert to NumPy arrays, and 2D histograms also you can make out of this. And this way you can like wind speed and directions also you can visualize this way. So once you get first, so the way this is the procedure to read a netcdf file. First you read it using OpenEX, then get the root group, and from there you can query which all multidimensional arrays are available in that root group. So then you can read all those groups one by one and then visualize that data. So remaining steps are similar to other things. So this was how do we read and write a netcdf file. So next we will continue with today's portion. So anyway, these are the same things, same libraries, then setting up the library. So now first thing, let us see that how can we improve the visualization of image. Suppose if you are seeing any single band image, you will see that the contrast of this particular image may not be good. Like suppose I am opening this file. If I visualize this image, so this image looks like this. So you can see that the contrast of this image is not so good. So let's try to improve the contrast of this particular image. So one approach may be like we can, if you see the histogram of this image, we can see that the data will be normally distributed. And suppose if you want to clip the outliers, like suppose we will calculate the standard deviation of this data and we will clip the pixel intensities which are beyond the 2 sigma level. So sigma is the standard deviation of entire image. So what we are doing, we are calculating so similarly, like suppose we can calculate the mean or standard deviation of the data. Then what we can do, we can like we will clip the pixels which are beyond from the mean 2 sigma left side and 2 sigma right side. So the pixels which are outside this range, we are just clip those to their minimum limit. So first for that, what we are doing, we are calculating the mean of the data. Mean can be calculated by calling np.mean. So np.mean, if we call on that data, so we'll get the mean of that data. Similarly, we can get the standard deviation. So that is called sigma. So mu and sigma we are calculating. Then if you multiply it the sigma by 2, we get the 2 sigma. So as we explained yesterday, so when plotting the data, we can specify like when we are calling the plt.im show. Anyway, here we are not changing anything on the data. While just plotting the data, we are just specifying the vmin and vmax, like the pixels to be clipped in this range. So vmin, we are specifying mean minus standard deviation. So mean minus 2 sigma and maximum to be mean plus 2 sigma. So anything beyond this range will be clipped to these vmin and vmax values. So let us see these two images. So in first, we are plotting the image without any. So here the image will be displayed to the default minimum and maximum values. So it will all the grade levels from minimum to maximum will be displayed here. But in the second plot, we are just clipping the values which are beyond 2 sigma from the mean. We are clipping those values out. We are just clipping the outliers. So suppose if we see this, so here you can see the difference. Now the contrast of this image is a lot improved compared to this image. So here, because we have clipped the values outliers, so values which are beyond the 2 sigma from the mean are being clipped. So this way we can, this is the one way to improve the visualization of the image. Then like there is another standard way of improving the visualization, that is called percentile. Like so we clip the values which are beyond the second and 98th percentile. So those all values can be clipped. So for that, suppose I am calculating the second percentile of the data and 98th percentile of the data. So then later on we are calling the function called np.clip, or even directly on this also we could have called directly even on this also, like vmin and vmax we could have specified. But there is another way, like we can call the function in data itself. You can clip before calling the plot function. So there itself, data itself, we have clip like np.clip data, and a mean we want the mean value. So the values which are below the minimum value will be promoted to what this mean value, and values which are above the maximum value will be clipped back to this 98th percentile. So this way we can again improve the visualization of this image. So a percentage value can be set to clip the outliers. Using percentile clipping can be particularly important for visualization by creating a smoother color distribution. Like if you clip the values in 2 to 98th percentile, so it creates a smoother color distribution. So let us see now how does the image look like. So same image when clipped to second to 98th percentile looks like this. So this was our original image. Then this, when we clip to 2 sigma level, then this is 2 to 98th percentile. So this way you can see that how we can improve the visualization of the image where the contrast of the image is very low. So this way we can visualize the the image. We can improve the visualization. Now let's the same thing. Now we will see that how do we subset a raster using its real world coordinates. Suppose what we mean that once you downloaded an image from the internet, but the image size may be very huge, but you may be interested only in a particular subset. Your area of interest may be very small area. So instead of processing the entire image, so before starting the processing, what you may require to clip to certain extent. So let us see how do we clip the image using, suppose if you know the coordinates of your area of interest, so then you can clip the image to your area of interest. So like here I have the same image, list 3 band 4 image. So this is I have specified the file name. And similar way I am just opening the file for reading. Then first I am getting the geo transform. So like geo transform of image, then GT, if I see, these are the geo transforms. Now if I see the coordinates of my image or lat long of the image, these are the latitudes and longitudes of image. These are the extents of my image. You can say that upper left corner starts from 79.24, 29.542. Like if I see upper left to bottom right, 79.542. So the extents of my image are from 79.24, 29.50 to 79.50 to 29.24. Sorry, 29.50. So these are the extent of my image. Now suppose if I want to clip it, like the latitude of my image varies from, if you can see, 79.24 to 79.50 longitude, sorry, and the latitude is from 29.24 to 29.50. This much area is covered in my image. Now suppose I want to subset this image to some my area of interest. So my area of interest may be 79.30 to 79.40 in longitude and 29.25 to 29.35 in latitude. So this is my area of interest. Now I will be clipping this image to these extents. Okay, so now first thing what I need to do. So first thing, I am converting these. I am converting from real world coordinates to image coordinate system. So for yesterday we discussed about converting from the image coordinate system to real world coordinate system, that was using Jidal transform. Today now we are doing the reverse. So what we are doing, we are trying to convert from the latitude longitude to the line number and pixel number. So for that there is a function called inverse geotransform. So first thing what we need to calculate the inverse geotransform for our given geotransform. That can be done using Jidal.invert geotransform of the or GT. So first we convert it, calculate a inverse geotransform. Then we are just applying apply geotransform. Then it is the same thing. Like first we need to calculate the first step, like yesterday. So if I see this inverse geotransform, then I see. So now you can say that this is our inverse geotransform. Now if we apply geotransform on this inverse geotransform, so with the help of this we can convert real world coordinate or latitude longitudes to pixel number and line number. So like I'm doing it here, offsets Jidal.apply geotransform. To this I am passing the arguments like inverse geotransform and which coordinates I want to convert, like subset extent 0 and 3. So like these are the latitude, first latitude and longitude, long and lat of the lower left corner. So this can see that this this coordinate like 79.30 and 29.25. So the pixel number and line number of this pixel 79.30 and 29.25 is pixel number 242 and line number 686. Similar way we can calculate it for the, now anyway the line number and pixel numbers will be in integer. So we are just converting these floats to the integers. So like we are calling by calling the map function and integer, converting them to integers. So if you see the offsets, so it says 242 and 686. So similar way we can do the same thing for the lower right corner. So lower right corner is like subset extent 1 and subset extent 2. So then we are the same thing converting. So in our image coordinate system, our area of interest is from line number pixel number 242 686 to 686 1131, right? So by this we can calculate like how many number of rows and how many columns we need to read. So by calculating y offset 2 minus y offset, and similar way x offset 2 minus x offset, we will get that how many rows and columns are falling in our area of interest, right? So what we have done here, so anyway first we decided that this is our area of interest. We know their real world coordinates. So these real world coordinates we converted back to the image coordinate system like pixel number and line number. So once we calculated the pixel numbers and line numbers for our top left and bottom right corner, then we subtracted these. Then we by this we get the how many rows we need to read and how many columns we need. How many columns and rows will be there in our area of interest that we calculated. Now we will see how do we subset that. So subsetting is like the same array. So data equal to ds, our original data set, dot read as array. So read as array, if we don't pass any argument, it reads the entire image. Now actually we can pass multiple arguments to the read as array function. Like first argument is x offset and y offset, like from which pixel number and line number you want to read that array. X offset is pixel number and y offset is line number. So from where you want to read and how many rows and columns you want to read. Right. Now here what we want to read from the initial x offset and y offset. So 242 686 from this location we want to read, and how many 686 rows and 1131 columns we want to read. So that we have specified here. So data equal to ds dot read as array, x offset, y offset, and number of columns and rows what we calculated in our area of interest that we are passing to it. And now if you see the data dot shape, it will be like 445 by 444. Now let us visualize these both images together. Like this is our entire image, because we are calling here ds dot read as array. This will read an entire image, and in the data we have our subsetted image. So let us visualize these two together. So now you can see that this is our original image and this is our subsetted image. So some portion somewhere here. So this area we have clipped into this image. So this was our original image, and somewhere area from somewhere here 444 to 242 to 686. So put 242 means, so somewhere this area. So looks like this area we have subsetted to this image. So here you can see that the size of this image is 1151 by 1151, but here this size is somewhere around 400 by 400 approximately. So you can see the size of difference. So this way we can subset the image to your area of interest. So here this much area we are plotting it here. So this way you can subset an image. So now suppose if you want to write this data back to the disk, because right now we have just stored it in the memory only. So for that we need to first because the geo transform of the new image will change, right? So that's GT subset 0 we are putting with replacing with the subset extent. So now if you see the subset of this, like geo transform of this image will be like starting from 79.3 to 79.3 comma 29.252, because these we have clipped from this point onwards, and anyway resolution of the image remains same only. So everything we have copied from the original geo transform, but only the coordinates of the coordinates of origin pixel, like 00 pixels coordinate, just we have replaced here. Now other things remain same only, like we are creating a destination data set. Then we are calling the create method, and we are giving it the name subset.tif, the number of columns and rows, then one band, then setting projection of whatever we are copying from ds.get projection, same projection system we are setting. Only while setting the geo transform, we need to set the new geo transform what we have calculated here. Then other things remain same, like get raster band 1, and then write array, then flush cache and run. So if you see here, now one subset.tif file must have been created in this folder. So a subset.tif file got created, live of size 44 by 44. So then you can visualize it using, anyway this looks very dark here. So this same image you can visualize using some software, or directly in Python itself you can read it. Now this is the case when we knew the extents of our image in real world coordinates. The way was like, actually the same thing you can do with GDAL.translate as well. So now the second case keeps coming, like when you want to subset the raster using line number and pixel number. So now suppose you don't know the you don't know your area of interest in latitude in terms of latitude and longitude. So you just know the line number and pixel number. So you want to extract from this line number and pixel number to this line number, this pixel number. So same thing, like you can, so here you can do it. The same thing can be achieved using like GDAL.translate. So like first I am opening the data set for reading, then I can call the GDAL.translate. So GDAL.translate, in this I need to pass the argument like subset.tip, in where I want to save my destination file name, source data set and source window. Like it means that from this 900, 400, from the pixel number 900 and line number 400 to 200 pixels. So from this portion I want to read 200 pixels and 200 lines. So this way, by using GDAL.translate, we can subset if we know the line number and pixel numbers. Now if we plot these both images together, so you can see that this was our original image, and we were knowing that we wanted to read from the pixel number 900 and line number 400 to 200 by and 200 pixels in X direction and 200 pixels in Y direction. So this way we can see that this was the entire image, and from this 200 by 200 image we have clipped. So only this portion of this lake got subsetted. So this way, either using GDAL.translate or through that way, you can subset an image. So same thing, like same whatever we have done previously, same thing, like if you know the real world coordinates of your image, so that also can be subsetted using GDAL.translate. So when you know the line number and pixel number, then you need to pass the argument like source win, src underscore win. Otherwise you need to pass the arguments like projected window coordinates. So like here same thing I will be calling GDAL.translate subset.tip and the original data set, then projected window. So here I will be passing the like my origin, like I want to clip it min x, then min y, min x, max y. Actually the sequence is like minimum x, maximum y, like from the top left to bottom right. So max x and min y. So I need to specify the arguments, my area of interest in this sequence, min x, max y, max x and min y. So if I do this, then this gets subsetted. Now suppose if we visualize both of these two images together, so this way you can see that the same operation what we did last time. First we converted these manually, we converted latitude longitude to pixel number and line number. Then we calculated the difference between those two for calculating how many rows and columns we need to read. Then we read these many rows and columns from that X offset and Y offset. So same thing, just you can use GDAL.translate also for achieving the same result. Like there you need to specify if you want to extract by pixel number and line number, then you can pass on the argument src win. Otherwise you can say projected window. So this way you can subset a raster using GDAL.translate. Next, let us see how do we resample a raster. So resampling or regridding is another common data manipulation operation. We often need to regrid data from different sources to use them within a same tool. So a typical example is like, suppose sometime you want to do some analysis with the DEM. So the DEM may be at different resolution and your original or the image on which you are doing some analysis may be at different pixel resolution. So suppose you want to do some analysis by combining both of these together. So first operation what you need to do, you need to bring them to the same resolution level. So that will be the requirement for resampling. Like you have the data, so you have data from different multiple sources, like at different resolutions. So dam may be at the resolution 30 meter, and your image may be, suppose if you have taken the sentinel image, so that may be at 10 meter resolution. Now you want to do some analysis using these two images. So now for doing the analysis, you first need to bring them either 10 meter, you need to resample it to 30 meter, or 30 meter pixel you need to resample it to 10 meters. So that may be the requirement. Then for doing the interpolation, like interpolation means, because for some pixels we are calculating the value for the pixels where the value is not available, so we need to apply some interpolation techniques. So there are different interpolation techniques available, like nearest neighbor, bilinear, cubic spline, average, and so on. So these are the different resampling techniques for regrading the data. Change the spatial resolution of raster dataset and set rules for aggregation or interpolating values across the new pixel size. So these, by any of these algorithms, we can calculate the values for the new pixels. So like here you can see that this was our original image, and we wanted to resample it to a coarser resolution or bigger cell size. So what we may do, like these 4 pixels we may average, so we can put the average of these 4 pixels into a single value, or so this may be, depending on these algorithms, the value of this particular pixel by combining the values of these 4 pixels will be calculated, maybe depending on the algorithm used. And the same thing can be like, suppose if you want to convert a coarser resolution image to the higher resolution image, like 68. So 68, initially there was a 1 pixel only, pixel size may be like 120 meters. So if you resample it to 30 meter, then all 4 pixel may have the value of this 68. The next 4 pixels, this 70 value. Then 69 gets replaced in these 4 pixels. So in these two images, if you see, the extents are same only, but the number of pixels have increased 4 times in this. So this way either you can oversample or undersample. So like here we can say that these 4 pixels are the extents of these two images are same only, but these 4 pixels got converted to a single pixel. So we have converted to a coarser resolution image. Like these average of these 4 pixels got replaced by a new value. So these 4 pixels got replaced by a new pixel. The value of this new pixel is being calculated by the average, maybe the average of these all 4 pixels. So this way either you can upsample or downsample. So there are different techniques for doing this. Now let us see how do we do this using GDAL. So first I am opening the same file, same thing like ds_gdal.open. Then I am reading the first band of that array. Then original data, I will say that original data. So I have read entire data from my image. Then if I see the shape of this image, this is 1151 by 1151. Now suppose I want to convert, I will calling it, now I want to reduce the pixel size. So in the same area, suppose initially there were, like if you see the example of this, so initially in this area there were only 9 pixels. Now I wanted to create it like final resolution. So in the same area I wanted to create instead of 9, 36 pixels. Or this I'll be calling the final resolution. Or suppose here there were 36 pixels. These 36 pixels I wanted to convert into just 6 pixels. So 24 pixels to 6 pixels. So 1/4. So both things I can do here. So now suppose if I want to upsample, or I just want to reduce the pixel size. So for that we will calling the same function called band.read as array. So we have first fetched the one band from the raster. Now there is a function called band.read as array. So if you don't pass any, that actually band read as array takes multiple arguments. You can read about that. So band.read as array, if you don't pass any argument, it reads the entire image. Otherwise, like you can specify x offset, y offset, and how many rows and columns you want to read. And there are another options like you can say buffer x size and buffer y size. So if you pass these two arguments, what it does, like whatever your original image will be converted to this size. Like suppose if I am passing buffer size, so my original image size is 1151 pixels in X direction and 1151 pixel size in Y direction. Now suppose if I want to reduce the size of pixel by half, so instead of 1151 in the same area, now I want to fit 1151 into twice the pixels, because I have reduced the pixel size in X and Y direction by half. Now the number of pixels in the same area will be doubled. So here I am passing the buffer X size argument to be 1151 into 2, and similarly buffer Y size is equal to 1151 into 2, and then the resampling algorithm what I wanted to use, GRA bilinear algorithm I wanted to use for resampling. And the same thing now suppose if I wanted to create a coarser image from this image, like I want to increase the size of pixel. Increasing the size of pixel means suppose I wanted to reduce the resolution of the image. So the same thing like band.read as array, buffer X size 50. So now 1151 pixels will be resampled to just 50 pixels. 50 pixels in X direction and 50 pixels in Y direction, and the resampling algorithm is nearest neighbor. So this way we can resample, upsample or downsample our image just by using the read as array function in GDAL. So now if we plot these all images, so I am here creating 3 subplots in a plot. In one first plot I am plotting the original data, and in the second plot I am plotting what is called finer data, where we have reduced the size of pixel, or we can say the increase the image resolution. Anyway, because here we are not adding any new information to the image. New information is not getting added to the image. We are just changing the size of image so for the convenience of calculation only. So anyway, we are not adding any information to the image. And the next is coarse resolution image, where we have all the images are covering the same extents, but number of pixels in all these images are differing. So let us see that how the resampling changes our image. So you can see that this was our original image. Now so in this 1151 by 1151 pixels were there. Now we have just doubled the number of pixels in our image. Anyway, no new information get added, so you don't see much difference between these two images. But number of pixels you can slightly make out, like there were 1000 here, in the same area 2000 pixels are there. And when we have made it 50 by 50, so you can see the difference. So here, because of the coarser resolution, now features are not discernible quite clearly, are not visible clearly. So this way we can resample our image. So same resampling, like instead of using this band.read as array, same resampling can be performed using GDAL translate as well. So now we will show that how can you use GDAL translate to resample an image. Like dias.get transform. So this is like, if you see the resolution of our image in X direction is 0.002 and in Y minus 0.002. Now suppose if I want to make it 0.004, or I want to double the resolution in X direction, like I wanted to make a coarser resolution image. So same thing, like I can do GDAL dot translate, then destination file name, then our original data set, and resolution in X direction. So initially it was 0.0002. Now I want to convert it to 0.0045. So I am making the coarser image, or number of pixels in the image will be reduced. So then the same way in the Y direction. So just if you see GDAL.translate, and now if you see this, so here you can see that we have reduced the resolution. Initially there were 1151, now 500 pixels only are there in this. So this way with GDAL translate also you can resample your image to your requirements. In similar way, now suppose instead of specifying the X resolution and Y resolution yourself, now you suppose you know that my like the image on which I wanted to analyze it, that this has this width and height. So you want the resolution of the cell to be calculated automatically by GDAL itself. So then into the GDAL translate you can specify two more options, like width and height also you can specify, like this image should be resampled to this width and height. The extents of the image remain same, only the height and width will change. So accordingly, height and width we have fixed, so accordingly the image spatial resolution will change, right? So this way now you can see that this image is size of 500 by 700 or whatever, 700 by 700. So this image resampled to this particular size. Here the pixel spacing or pixel resolution calculated automatically by the GDAL translate. Similarly, you can resample it by relative size, like you want to make just 30% of the original in width as well height. So width percentage and height percentage also you can specify. So here you can say that 30% it got just 30% of this 1000 got converted to 300. So in GDAL supports another format called virtual raster table or VRT format. So the VRT format of GDAL allows a virtual data set to be composed from other GDAL data set with repositioning and algorithm applied, as well as various kinds of metadata alerted or added. So now what is happening now, suppose you have two some 3 or 4 bands of your image. Now suppose if you want to calculate a NDVI image from your 3 or 4 or 2 or 3 bands, whatever, or suppose you have 4 band image and you wanted to create a new image which contains some multiple indices like NDVI, NDWI and 3-4 images. So instead of reading the image and calculating the NDVI and then saving to a GeoTIFF image on the disk, so this is like just wasting the space. So for that there is a special format in GDAL that is called VRT format. So in VRT what you can do, whatever computations you are doing, so those computation can be as those computations or this instruction for doing those computation can only just be stored in an XML file. So instead of storing the entire GeoTIFF image, just instruction for deriving that image just can be stored in an XML file, and that calculations can be done on the fly using GDAL by GDAL. So this way we are saving on the space. So that is what we call. So VRT is a custom format supported by GDAL that is similar to something like you can say the links or shortcut, like when suppose you have a big data folder, so the link to that you can create somewhere else, right? So similar way we are just writing some in XML the steps for deriving that new data set. We are not creating the data set and saving to the disk. Instead of we are just storing in XML the instruction for deriving that data set from some source data sets. So that is what we call VRT format. So this way we are saving on the disk space. So let us see how do we create a VRT image from our image. Suppose we have a nainital.tif image. So for this image we want to create a VRT image from this. So that like anyway generally same image we will not be saving in VRT, but like you wanted to do some calculations on that image, and instead of saving that entire new image like we were using in create copy, we just wanted to save the information in XML file so that on the fly this new image can be read. So here I am doing VRTDS GDAL.build VRT. So you can call this function build VRT and just name of the destination Nainital VRT.VRT and the source destination. For this data set we are converting it to the VRT data set. So if I see this and flush cache, if I do now, here you will see that nani_VRT.VRT a text file in XML format might have created. So now if you see the same image, instead of being saving an entire image, so the few instructions like how to interpret this, how to calculate this image has been stored here, like VRT dataset raster size 11511 by font. So like source data access, this is this. Then here you get a simple source. So relative to nainital.tif. So there, like here we can write some calculations also, like do the operation on this band 1 and band 2, then this. So instead of writing the entire image, just XML representation of the steps to be followed to make a derived image are just can be stored in this VRT image. So this way, when you are want to save the disk space, you can save in a VRT format as well. So now let us see how do we reproject a raster. So like what is the requirement of reprojecting a raster? There may be numerous use cases when raster data needs to be reprojected. Like these are the cases. A region of interest is too large for analysis within a single UTM zone. So if your region of interest is too large and you want to do analysis in a single UTM zone, then you need to reproject your image to some GCS or something. So, or it may be like putting together DEM from different sources. So the DEMs what you have got may be from different sources and they may have different projection system. So if you wanted to do analysis by combining, suppose if these two DEMs or two images which are in two different projection system, then you need to reproject them to a common system, so that only then you can do the analysis. Then suppose you want the similar way you wanted to combine data from the different sources, in that case also you need to reproject the data to a same common system. Like here I have a DSM or digital elevation model for this region. Now let us see, this is the image. Now I have, sorry, this is not required. So say same band 4.tif. Now I will be projecting this to some UTM coordinate system. Now if you see this band 4.tif, this image in GeoGCS coordinate system. Now suppose if I want to project it to UTM 45 north. So for that, first I am creating a spatial reference system like OSR.spatial reference, then set projected coordinate system to be UTM 45 north, and well-known GeoGCS for this corresponding to this projection system with GeoGCS is WGS 84. I have created a projected coordinate system. Now if I see this projected coordinate system to WKT, so it says that this is a projected coordinate system and the GeoGCS corresponding to this is this WGS 84 EP or EPSG 4326. Now anyway, I am opening my image. In this I will getting the projection. Now let us see that how do we reproject this image from GeoGCS or geographic coordinate system to a projected coordinate system called UTM 45N. So for that there is a function called, actually there are functions like jital.reproject and other things. So for this, instead of writing the entire image, I am calling the function called jital.autocreate warped VRT. So instead of creating a new directly GeoTIFF image, we are just creating a VRT. So for that the function is jital.autocreate warped VRT. So what it does, it will take the original image, reproject it to the coordinate system, to the new projection system which we are specifying here, and then that will be saved as a VRT. So this auto create warped VRT takes these arguments, like first is your original or old data set which you want to reproject. Then if you pass second argument to none, so it takes the like source projection system to be, if your original image also is not projected, then you can pass it the projection system. Otherwise, if you are passing it to none, then it takes the projection system of our source data set. Then the destination projection system in which you want to reproject your image. So we wanted to project it to this new CRS. So we have created a new CRS here. So that, but it takes in WKT format. So that CRS we are just converting into WKT, exporting to WKT. Then which resampling algorithm you want to use for reprojection. So here we wanted to suppose nearest neighbor. So this way we can create a warped DS. Now let us see that this has created an virtual data set. It has not created an actual data set. Now suppose here let us see that original and reprojected image together in a plot. So this old underscore DS is our original image and this VRT underscore DS is our reprojected image. So now if you see, so you can see that this was our original image. When we reprojected it to a UTM, so this got slightly tilted. So this way we can reproject an image using warped VRT. So auto create warp UART you can use for, or there are other function like GDAL dot reproject image and so on. So multiple functions are available for reprojecting image. Actually, there is another utility called GDAL.warp. With warp also you can reproject your image. That we will be covering tomorrow. So now let us see stacking raster bands. So stacking means generally actually what happens, suppose if you are downloading the data from any data provider like from the ISRO Bhuvan or NASA's website. So generally what they do, so they will be giving the data like different bands in different files. Okay. Now suppose if you wanted to combine these different files together, stack them together and create a composite image from these different bands all together. So this is the requirement generally comes because when you download the data from any like from ISRO's Bhuvan or NASA's website or even ESA's website, they give the different bands in different files. Now let us see that how do we combine these different files together to make a single RGB composite or any false color composite. So in this my L33, in this folder, these are the files like L344. So in this folder you can see that once if I download the data from the Bhuvan, I will get the data like this. So these all 4 bands in 4 different files. Now suppose if I want to combine these all 4 bands together using and make a single composite raster. So let us see how do we do this. So this is my directory. So anyway, whatever code we are showing here, this code may not be the most efficient. This may not be the most efficient way to do. So this is we have tried to make it as simple as possible. So there may be multiple ways to do the same thing, and you can do it in less number of lines and more efficient code you can do. But this may not be suitable for production environment, but this is just for demonstration. So this way you can see this and you can implement it the way you want. Like here I have stored all the file names, though I can extract these file names directly from the directory as well. But here for simplicity, I have just stored the names of these all files like band 2, 3, 4, 5 in a one array. Okay, now I will be looping over these array one by one and combining them together. So next I am creating a list in which I will be pushing all these data together, and later on we will combine these all together. Now here what I am doing, I am looping over these file names. So these 4 files are there together. I am stacking all these 4 files together in a single file. So what I am doing, for file in files, ds equal to zidal.open file. So I am opening these files one by one and fetching the band in band 1 from all of these images one by one, because anyway I know that these images has only single band. Then fetching the data from that band, and that particular data I am pushing to my list, right? So this is quite simple. So I have iterated over all these files one by one and pushed that data from all these images to a list. So now I see this img underscore data. So now this has 4 arrays in this. So this has 4 elements. So every element is an 2-dimensional array, or like image data 0. So this is the image 0. Then next element is image 1, band 3, band 4, band 5, and so on. So these are the images. Now suppose if you want to visualize these images together, so these are like all these bands together, like this is the band 1, 2, 3 and 4. So these are these 4 bands. Now let us combine these together. So anyway, generally, and what assumption we are making, that the extent or the size of all those images are same. That is generally true for if you are downloading from the source, and all those images cover the same extent. They have same projection system and same CRS as well. So here this assumption we are making. So anyway, this destination, we are creating a destination file with the name say rgb image.tiff, and we are just calculating the height and width of image data 0 from the first image itself, from first image, because then we are assuming that the height and width of all other images also will be the same. So calculated this. Then same thing like what we saw in the morning, gdal.get driver by name gtiff and driver.create. So destination file, then width and height what we calculated here. Then because suppose if you want to create just 3 bands or 4 bands, because here we have 4 bands, we'll pass it that like number of bands to be 4 or 3, whatever you want. Like if you want to copy only 3 bands, you can make it 3, or if you want to make 4, 4. Then E type is GDAL dot unsigned integer 16-bit. In morning, people were asking like how do we create 16-bit image. So here you can say that you can pass the data type to be GDAL dot GDT, so unsigned 16-bit integer. Then we are setting the projection and copying the projection from any of the last image, like our destination data set dot set projection, get projection, and get geo transform. So we are creating a destination data set and setting the projection on this. Then though we have set everything there, but we have not copied the data. So for copying the data, now I am going from like range, because we want to create a 3-band image only for I in range 1 to 4. So one by one we are fetching that particular band from the destination data set, and in that band we are using the write array from that image data. So in image data we have read all the data, so we are writing this image data to this band. So this way. So once this is done, then we are finally flush cache and delete destination. Now here one RGB underscore img.tif file must have been created. So RGB underscore img.tif got created here. So now this image, suppose if you want to visualize like how does it look like. So ds. Now suppose if I want to read this image, then ds.read as array. So anyway 3 bands only are there in this image. If I don't pass this also, it becomes same data. So this way you can see that we can stack images together. So this is stacked image. So this way we can make a stack of images by combining all individual bands together. So then once this is done, so this is, thank you very much, this much for today. So just a quick recap. So what we learned today, so we learned how to read a file. Then using GDAL, like the basic function for reading a file is read as array. So read as array is a very versatile function. So read as array can be used for multiple cases. Like suppose if you have a very big image and your area of interest is very small. So instead of processing the entire image, you can just clip your image to your area of interest and then do processing on that. So for clipping your image, there are multiple options. Suppose if you know the real world coordinates of your image, so either you can directly use GDAL translate, or you can use this read as array function also for clipping your image. Then we talked about VRT dataset when you don't want to save the entire image, like so you have derived some new image from your existing images. So instead of saving the image to entire new data set to the image, you just wanted to save it to an XML format so that the calculations can be performed on the fly and you are just saving on the disk space. For that you can create a VRT data set for your image data set. And then we saw how do we reproject image using auto warped VRT. So that's all for today.